Okay, hello and welcome to a quick Matplotlib introduction on visualizing data. So this is mainly aimed at my fellow undergraduates who are maybe interested in learning some more Python for labs, and those who are interested in how I use this to create my figures for my lab reports. So as we progress, I will explain each line of the code, tell you what it does. So let's start off by importing the modules we need. So the very first one is obviously from Matplotlib, import pyplot as plt. Okay, so it's just a shorthand for when you import and call it. Instead of writing pyplot, you just write plt. It's just a lot quicker. So we're also going to use NumPy. Now I use NumPy when I have very large data sets, say loads of measurements. I'd create them all into a single NumPy array. And then if you need to do any operations on it, such as squaring, dividing, I don't know, taking the sign of it, you just do that operation on the whole array, and it does that operation on every single measurement, on every single data entry. So it's a lot quicker than doing it entry by entry, which I recommend against doing, especially when you have hundreds of measurements. So now we've got pyplot and NumPy. The next is, this one is, well, not optional, but if you want to carry out model fits, such as linear regression or fitting any kind of function to data, you need a fitting algorithm. Now I use ODR. It's a package from SciPy. So if we just import that, so from scipy.odr, import ODR model and real data. So ODR stands for orthogonal distance regression. It reduces the distance of the model from the observed data points in both the x and y directions. So if you think about that in terms of Pythagoras, x and y, right angle triangle, that will reduce the overall distance from the point. And I use this over packages like curvefit because that only considers errors on the response variable, on the y variables, and it completely negates x errors. So if we consider both x and y errors, your model will probably be a lot more representative of the data that you've passed it. Okay, now we've got all our modules imported. Let's begin with the actual process of visualizing it. So in this example, suppose we want to represent some sort of sinusoid. So first of all, we need our, let's say I'll call it our measurements. So as I don't have any measurements on me at this time, I'm going to use something called arange from the NumPy package. So this just generates an array of numbers for you. The first input is the start. So let's say we want to start at -5. The second argument is where you want to finish. So -5 and 5, make it nice and symmetrical. And the third argument we give it is the step. So how far apart the measurements are spaced. So if we want a nice refined smooth curve, we want a rather small step relative to the distance between them. So I reckon 0.05 will give us a smooth curve. Again, if this was an actual measurement that we were using with real measurements and errors, we wouldn't use this. We'd simply import the data from maybe a CSV or an Excel or a notepad. I can show you how to do that in another video, but for this we'll just cover the basics on how to actually get a plot, how to physically get something to show up in the plots tab here. So now we need to define our y function, what are we actually going to do to this data. So I mentioned we're going to be taking a sinusoid, so let's say y equals np.sine. This is just taking the sine of it. Now let's say we want to do sine of, I don't know, x squared. So we've got x and our y. We're almost done. The rest of it is just cosmetics, really, to make the graph look better. So let's say we call this, it's almost like a tuple, or tuple, however you want to say that. So we've got fig and we've got ax equals, now we're going to call it plt.subplots. Subplots is very powerful, but you can do a lot of things with it. And we'll say dpi equals 1200. This just makes it a nice high fidelity plot. There's a lot of other things you can put in arguments, such as n rows, n cols, which stands for the number of rows and number of columns. If you want to make, say, 2 graphs next to each other, or maybe one above the other, or even more, that's what it's handy for. I could show that in another video, but again, we'll just cover the basics for this one, just a single plot that we want to show. So, we've got a bunch of x data points, so let's show those data points on a graph. So we use that using ax.scatter. So we've got our x data, our y data, and let's say the marker. This is usually a string, let's call it an x, so these markers will be crosses. Line width is the width of the line of the marker. You don't want them too big, don't want them too small either. So let's just say 0.2. Again, you can customize all of these any way you want. You simply change the values and then rerun the code and see if you like it. But I'll just use these for now. Color, let's make it black. S, now this is some value that alters the opacity of the points. We'll see what that does later on. And then label, this is quite handy as well. You can add labels to legends to your plots. So let's call this observed data. Okay, this line of code here, all we've told it to do is make a scatter plot of the x and y coordinates with some marker x, a rather thin line that's black, and we've labeled these as observed data. So the next line is if we want to plot the actual function. So at the moment all we've done is we've plotted the x, y coordinates of these data points here. That's all we've done. So if we actually run this now, let's run it first to see what it looks like. If you want to show your plot, you'll end it with plt.show, open close parentheses. So let's just run the code and see if it actually works. Right, there we go. This is the plot that we've got. So as you can see, it's worked. It's successfully compiled it. So we've got lots more things we can do to this. We can add x-axis titles, y-axis titles, an actual title, like a main title. We can add error bars. We can add the function fit. So let's try and do that now. So to visualize the plot of the function, we will use plot for this. So ax.plot. So we've got our x data, we've got our y data. Let's choose a color. Let's say red. We'll call this one sinusoid. Line width equals, let's say 0.5. Okay, let's run that code and see if we get a plot on top of it. Okay, there you go. Simple as that. Not the most elegant plot, but it's progress. It's getting better. So as you can see, that's exactly what we expected. Now, we've written labels here and labels there, but they haven't shown up. That's because we actually have to call another thing. So we'll write ax.legend. Now, lock means location. You can be specific and write literal coordinates of the grid space here, but you can also use predefined positions. So if we say upper right, obviously it'll be in the upper right. We'll have to make it a bit smaller because it might cover up these points here. Usually in that case, I define the location using coordinates and place it outside of the plot, because otherwise it'll lay over points and you don't want that. So if you want to change the size as well, we use prop equals. Now we use braces for this, and then in quotes size : 4. 6 is usually, I think 6 is the default size. 4 is a little smaller. Let's just do 6 and see what that looks like. Okay, So now that should give us a legend show up in the upper right corner if we've done everything right. There we go. So obviously you can do upper left too, same with, yeah. So that's essentially the basics. Oh, a few more things we can do actually. Let's add some labels. So if we want to ax.set underscore title. Okay, what should we call this? I don't know. Sinusoid plot. Ax.set underscore x label. Just call it x. And then ax.set underscore y label. Let's just call that y, just for simplicity. Okay, so let's run that again. There we go. So we've got labels, we've got labeled axes, we've got a title, we've got a legend. That's the basics for visualizing data. Now, the physicist among the audience hopefully noticed I didn't include error bars in this plot. So if you want to include error bars, it's a similar extension to what we've already done. You have to be careful because the dimensions of this array will have to be the same as the dimensions of that and that. And if you have, similarly, if you have y errors, they will all have to be the same dimension, otherwise it won't plot properly. Because you're essentially saying each point has to have an x and y coordinate, obviously, and they also have to have an x and y error, respectively. If we don't have a y error, then we can simply just nullify it and write y error equals none. So I'll show you the syntax for that now. So let's just say we only have x errors. So if we want to include error bars, it's similar to what we did before. Let's say ax.errorbar. So x, y. So that's the coordinates of each point. So at point x and at point y, we have x error equals, now the name of it, we did x underscore error. And we have no y error. So let's just leave that as y error equals none. Let's say line style, I always put this as none because I don't want them joined to each other because it just looks bad. Line width, let's say that's not equal to 0.1. Marker, we don't want a marker. We just simply want the error bars to go through the X because it's already got a marker here, so you don't want another one. Let's say the color is blue. Cap size, now that defines the size of the cap. I usually leave it as 0.5. And let's set a label as error. So let's plot that and see what it looks like. Here we are. So this is what I said earlier. So we've got a value error here. The lengths of the data 200 and the error 50 do not match. So this is to do with this error, this array here not having the same dimension as this. So if we halved that to get 2.5, let's half that to get 0.025. Now that should work. They should be the same dimension. There we go. Now you see it looks rather stupid, but you have your error bars. So there you go.